Molecular assemblers operate at the picometer scale, manipulating individual atoms using precisely controlled mechanical forces. This deterministic approach fundamentally bypasses the limitations of stochastic chemical reactions inherent in traditional chemistry. The concept, termed positional assembly, shifts manufacturing from bulk processes to precise atom-by-atom construction. The theoretical foundation relies on designing specialized molecular tools, or reactive tips, attached to robotic arms. These arms must be capable of positioning atoms with sub-nanometer accuracy onto a growing workpiece. This precision allows for the creation of novel materials and complex structures impossible to synthesize through conventional methods, representing a paradigm shift in engineering. At the nanoscale, thermal noise, known as Brownian motion, dominates, making uncontrolled reactions inevitable in liquid or gas environments. Molecular assemblers must therefore operate in a vacuum or a highly controlled non-reactive environment, or utilize extremely stiff components to overcome these random forces. Mechanosynthesis is the specific process employed, where mechanical strain is used to lower activation energies for desired bond formations. This ensures that only the intended reaction occurs at the designated site. This requires tooltips designed not just for positioning, but for applying specific forces, such as compression or shear, to facilitate the formation of strong covalent bonds. A molecular assembler is typically envisioned as a component within a larger integrated nanofactory system. The nanofactory provides the necessary infrastructure, including power distribution, feedstock supply, and centralized computational control. The assembler itself consists of highly precise manipulators, often resembling microscopic robotic arms holding specialized molecular tools. These tools are designed with specific chemical functionalities, such as radical abstractors or dimer placement tips. They sequentially add atoms like carbon or silicon to the structure being built, layer by layer, following a detailed digital blueprint provided by the control system. To achieve the required stiffness and positional precision, the components of the assembler itself must be constructed from extremely strong, rigid materials. These are often theorized as diamondoid structures. Diamondoid materials are carbon lattices similar to diamond, but engineered with specific geometries to prevent thermal drift and maintain positional accuracy during operation. These structures minimize vibration and maximize the force transmission efficiency from the macroscopic control system down to the atomic tooltip. This structural integrity is essential for ensuring the fidelity of the construction process, even when applying high mechanical strain to form new bonds. Molecular manufacturing requires significant energy input to break existing bonds and form new ones deterministically. Energy is typically supplied externally, perhaps through focused electromagnetic radiation or chemical potential gradients maintained across the nanofactory structure. The control system is highly complex, requiring advanced artificial intelligence algorithms to manage the simultaneous operation of millions of manipulators. This control system translates the macroscopic design file into a sequence of precise atomic placement instructions. It must constantly monitor and correct for any positional errors in real time, ensuring the final product matches the digital specification exactly. Raw materials are supplied to the nanofactory in a highly purified, often gaseous or liquid phase, ensuring no contaminants interfere with the precise assembly process. Simple molecules like methane or carbon monoxide serve as primary feedstock. These molecules are then broken down into individual atoms or small reactive groups by dedicated processing units within the factory infrastructure. These atoms are channeled through molecular sorting mechanisms to the specific assembler sites where they are needed. This highly controlled input system minimizes waste and maximizes efficiency in the construction of the final product, enabling near-perfect material utilization. The concept of self-replicating assemblers, often referred to as von Neumann probes, is crucial for achieving industrial-scale molecular manufacturing. A self-replicating assembler is designed with the capability to build copies of itself using readily available feedstock. Once a single assembler is operational, exponential growth allows for the rapid production of billions of identical units, leading to massive scaling of manufacturing capabilities. This replication process is governed by the same precise atomic placement rules used for building consumer products, ensuring high fidelity across generations of assemblers and enabling rapid technological proliferation. Applications span radical life extension and revolutionary material science. Medical nanobots, or nanomedical devices, could patrol the bloodstream, actively repairing cellular damage, destroying pathogens, or precisely delivering drugs at the molecular level directly to diseased cells. This capability promises to eliminate most current diseases and reverse aging processes by repairing telomere shortening and mitochondrial decay. In material science, assemblers could create materials with perfect structural integrity, such as flawless diamond cables or programmable matter known as utility fog, fundamentally changing resource scarcity and construction methods. The successful development of molecular assemblers is often cited as the technological trigger for the technological singularity, where self-improving artificial intelligence and exponential manufacturing capabilities lead to unpredictable, rapid change. However, the theoretical risk of uncontrolled self-replication, known as the gray goose scenario, necessitates strict safety protocols. If assemblers were programmed to consume biomass indiscriminately for feedstock, they could potentially convert the entire biosphere into copies of themselves. Therefore, safety mechanisms such as built-in kill switches, restricted feedstock access, and physical containment are paramount during the initial development phases.